Good evening, one and all. Myself, Yashvi Sheth, and today I will be taking the sixth live session for the course Basic Principles and Calculations in Chemical Engineering, taught by Professor Subrato Majumdar from IIT Guwahati. So, starting with this session, I will be starting with the brief of the lectures that were covered in week 6. So, basically, the lectures in the entire week is more or less it talks about energy. Okay, so what does this mean? The lecture, it starts with the basics of energy. What does the energy mean, and various forms of energy, and its applications. How energy is important. Calculations for energy is important in chemical engineering, and where do we apply it? So, what does energy mean? Just a second. Good evening, one and all. Myself, Yashvi Sheth, and today this is the sixth live session on the course Basic Principle and Calculations in Chemical Engineering, which is taught by Professor Subrato Majumdar from IIT Guwahati. So, starting with this session, we will be talking firstly about the brief of the lectures that were taught in the week 6. Basically, the entire week, what was focused upon was the terminology energy. Now, why does energy needs to be studied? So, in this week, we will study what is energy, what are its types, why it is important, where it is used, and in chemical engineering, how it is applied and where do we encounter energy, and also the calculations and any balance related to energy. So, what does energy mean? So, every now and then we talk even if we don't think of what energy mean, we sometimes uh, if we take the example of human beings, we sometimes say uh, my energy is very low today, or we may end up saying that I'm very exhausted, like I'm very feeling low in energy. So what does that mean? Like, for to survive our body, we give some external food material which is consumed so that our body is able to do work. Our body is able to do something for which some kind of energy, some kind of efforts from ourselves is needed. So similarly, to perform any natural process or any artificial process, you need some sort of energy. So where does this energy come from? It is coming from the utilization of some physical resources or some chemical resources, and so that the system is able to do some kind of work. So for example, if you want, there is this body, okay, and if you are applying force, so until and unless you apply some force which will be uh, stored in the form of some kind of energy in this uh, block, and by utilization of that energy it will be able to move in the forward direction, otherwise it will be steady on the floor. Also, like, for example, if I give you the example of real life industrial application, then what do? Very basic example would be you use steam you generate steam in boilers. And where do you use this steam? You use steam in the jacketed reactors to heat the system. Okay. So what do? You convert water into steam, and this what steam has some more energy. So what do? You burn a fuel and you transfer the energy of that fuel to water, which is utilized to convert water into steam. So there is this transfer of energy. So there are some basic properties of energy. As I said here, there is transfer of energy. So energy is just transferred in the form of heat flow, in the form of mass transport. Now, how is mass related to energy? So one of the most basic law that you know is Einstein's equation, like E equals to mc square, where c is the speed of light. So this is the amount of energy which will be generated if you burn this much amount, corresponding to the mass m. So energy is also related to any matter. Say, so any matter, it will have some corresponding energy. It can be transferred by temperature gradient in the form of heat flow, or it can be produced by some work. For example, work is nothing but force into displacement. So this is a kind of energy transport. Now this energy can neither be created nor be destroyed, and which was also termed by this equation E is equals to mc square. Even if any mass disappears from this earth, it will be converted into some form of energy. Yeah, so for example, if you are trying to produce steam from water, okay, so what you will do, you will supply some amount of energy in the form of heat to this system so that steam is produced. Now, not all the energy that you are providing is utilized to convert water to steam. There will be some amount which will be wasted. Now, wasted, what does waste mean? Waste means for this particular system, the utilization of energy is just to convert water to steam. So some amount of wasted means it is dissipated in the form of heat to the surroundings, and it might cause the temperature of the surrounding to rise. So there is just transfer. The transfer of energy here in this case would be first to produce steam, and second it would be, say for example, raise in surrounding temperature. So here you can see the total energy remains same. Whatever you have supplied, it is utilized in these two forms. It can be another as well. I am just giving you two examples. So it will be utilized in these two forms. And so we can say that energy can neither be created nor be destroyed. It can just be converted from one form of energy to another form, or it can just be transported through heat flow or by transfer of mass, or you do any kind of work. So this is also the first law of thermodynamics, that energy can neither be created nor be destroyed, and the total energy of the universe always remains constant. Even if any mass disappears from the earth, then what happens? It is converted to some energy. Now, there are various types of energy that any matter or any physical object that can have, or any system can have. It can be kinetic energy, it can be potential energy, thermal energy, electrical energy, chemical energy, radiant energy, etc. There can be many more, for example, mechanical energy, and so on. So if I tell you the meaning of each and everything, so some of the energies are very basic and you have learned about them in your schools also. So what is kinetic energy? Kinetic energy is the energy related to the motion of any body. Just a second. So it is related to the energy which is related to the motion of any body, which is moving at a speed of speed v, and it has mass m. So in that case, its energy would be the kinetic energy associated with that system would be half mv square. Now, so kinetic energy is related to the motion of any body. Now, similarly, there is one more term which is potential energy. So, what does that mean? Potential energy is the energy that any body or any object or any sort of material that possess, if some if it is taken against the direction of force, or which is stored. For example, if you uh, like gravity is in downward direction, this is the direction where gravitational force exists. So any object, uh, it will be directed to go in, or it will be attracted to move in downward direction. Now if you want to take this uh, object in upward direction, then you have to do some amount of energy, you need to apply some amount of force, you need to spend some energy to take this object upward. And whatever amount of energy that you spend in taking this object from, let's say, z equals to 0 to z equals to h, then that much amount of energy will be stored in that material, which will be utilized when it is allowed to move downwards, and so it will fall freely. So what will be the amount of energy that will be stored? It will be equal to mgh, like if I take in vertical direction against the force of gravity. Now next, terminology. Here I have mentioned about this earlier also. Work. So work is nothing but the transfer of energy on the application of some external force. So work is nothing but force into displacement. So if you apply any force and there is some amount of displacement of the object, then only you can say work has been done. Otherwise it will be zero. So now moving forward, so mainly any system can have these many, like basically it will have kinetic energy, potential energy, thermal energy, which is related to the body temperature. Okay, so mainly system possesses this much energy. So if you want to apply any energy balance, so what does a balance mean? I have earlier talked about this. So balance means accumulation equals to input to the system, accumulation in system. Okay, so any system you consider, input to the system minus output to the out of the system, output out of the system. So what will be the amount of accumulation? So that will depend on the substance. Okay, so whether it is utilizing, say for example, you have a system and it is a moving system stored at some height. Okay, so it will have some sort of internal energy which is due to the molecular motion, or which is also termed as molecular kinetic energy, and there will be some internal forces between molecules. Now what does this force result? If it is like if it is attractive or repulsive, based on that it will have some potential energy. So internal energy is associated with the kinetic energy plus potential energy of the molecules that it has. So it is depending on what material you are using. So internal energy is U. So if this is the internal energy, it has finally, because if you supply some amount of heat Q to the system, and if it does some amount of work, then this is the net energy transferred input minus output, and due to that there will be some change in the internal energy. So what is that change? This is nothing but the accumulation, and that will be final minus initial. So that will be accumulation. So final internal energy minus initial internal energy. Also, if the system as a bulk, it is moving with a velocity v, then it has some kinetic energy associated with it, which is known as kinetic energy. Like if the motion of this body is accelerating, okay, so in that case v will increase, kinetic energy will increase after the application of heat, so KEF will be more than KEI. So there will be some change in kinetic energy, and also if there is some change in height or so, there will be change in potential energy, which is potential energy final minus initial. So this is how you write the material balance. Now this there are certain laws in thermodynamics which are related to energy, and which are related to which can be indirectly or directly related to the terminology energy, and to apply further balances. So to know about what these laws mean, there are 4 laws. Zeroth law, it means that if any two bodies, say for example A, B, C, like there are 3 bodies, you can say that AB and AC are in equilibrium. So what does that mean? Say for example, A has temperature 100, B and B has like after equilibrium, A has 8, B has 80, C has 60. So now all these 3 are connected, okay, like at least these 2 are connected. So what does that mean? The temperature now has become steady. So if A and B and A and C are in equilibrium, then you can say that B and C are also in equilibrium, because since A is the mutual one which is connected to both, there will be some transfer from both the systems, and that is why the temperature or the final state it is that occurs, it will depend on both B and C. So you can say that B and C are also in equilibrium. So what does zeroth law state? If two systems are in thermal equilibrium with a third system, say for example A, then they are also in thermal equilibrium with each other. So here B and C are also in equilibrium. Now, first law of thermodynamics, as I said, energy can neither be created nor be destroyed. So this is the basic most statement of first law. Now, what does this imply? This implies that for if you take any system, so the major energies related to any system would be whatever you supply energy in the form of heat, whatever you take out work from that system, and there will be some sort of internal energy associated with this. So this is, and you can assume that there is no change in bulk kinetic energy and potential energy. So if you apply the material energy balance here, so what will be the case? Change in internal energy is nothing but Q minus W, and this is the statement of first law of thermodynamics. So whatever you are giving heat to the system and whatever work you are taking out of the system, the remaining energy that is left, it is utilized by the molecules of the system to change the molecular kinetic energy or to change the molecular potential energy. So there will be some change in molecular motion, or there will be some change in internal force also. So, for example, if you are supplying heat to the system, like Q minus W is positive. Okay, just a second. So since Q minus W is positive, there are chances that temperature rise occurs. Okay, because you are adding heat to the system. Now, as the temperature rises, the chances of the heat or the energy associated with this temperature rise, it is utilized to enhance the molecular motion. So molecules will be uh, um, more freely moving as compared to it was moving earlier. So this is the first law. Now coming to the second law states that as the energy is transformed from one form to another, more and more of it is wasted. So it is a kind of statement which shows that any system in this real world is not reversible. Like for example, what does reversible system mean? For example, if you mix water plus milk, so if once you mix water and milk, then you after mixing you will not be able to separate or distinguish between water and milk. So in that case, this is irreversible system. And ideal system is said to be reversible, where you can, if you change the say for example, water and milk are mixed, then if you are able to separate, then it will be a reversible system. So this is a kind of statement which shows that uh, all the systems in this nature are irreversible, and more the irreversible system, then uh, the energy which you are transferring, it is not utilized in the way you want. More and more of it will be wasted in some other forms. Third law of thermodynamics uh, talk about some entropy. Now we will talk about entropy further also, like what does entropy mean. So let's talk about that first, and I will come to this later. So entropy is nothing but uh, it represents molecular disorder and randomness. So let's take example of solid, liquid, and gas. So you can see that solids have more tightly packed molecules. Okay, now liquid have some lesser force, and they are more loosely packed, and gas are the least tightly packed. So here, if you look into the definition of entropy, then the molecular disorder or the randomness molecules have, it is least with the solid, and gas has the highest um disorder or randomness of the molecules. So you can say that entropy of solid is least and entropy of gas is highest. And if you convert any solid to gas, its entropy increases. So there is like this equation for entropy, d is equals to dq by t. So it also states that if any system has some amount of energy, then whatever amount of energy which is not available to do some useful work per unit temperature, because if you want to spend some amount of work, if you want to do some amount of work, you need to use some amount of energy from that system, and if you are not able to convert into any useful work, then that energy will be wasted. Okay, and that waste of energy is related to entropy. So this waste of energy is also related, you can say that uh, it also represents reversibility of system. So if any system has more entropy, then you can say that the system is more irreversible, because you are not able to utilize and do some useful work out of that system. So since we have understood what entropy is, so we can say that from the third law, any like say for example you have gas, and as I mentioned here, gas has the highest entropy, and if you move towards solid, then its entropy decreases. So as you decrease the temperature, gas will be converted to liquid, liquid will be converted to solid, and this means that entropy S will reduce. Now the at like as temperature decreases, entropy reduces, and based on that a law has been derived, like if you keep on decreasing the temperature till 0 Kelvin, then at that this much temperature, the entropy of that system will be constant, or because after that the further this molecules are most orderly arranged, so after that there will be no change. And also if there is a perfect crystal, then in that case entropy becomes zero. So this is the third law of thermodynamics. Now for any thermodynamic system, whatever the amount of energy that is associated with that system, or the heat content of that system, is nothing but known as enthalpy of that system, and the enthalpy has formula. So for example, you have some system and it has some internal energy, so that energy will obviously counted as the energy of that system. So enthalpy is H equals to U, internal energy, and since enthalpy is nothing but total heat content of the system, there will be some heat content which is due to some parameters of that system, which are pressure and volume. So enthalpy is H equals to U plus PV. And if you want to find change in enthalpy, if you apply delta, then delta H equals to delta U plus delta of PV. Now enthalpy is always calculated at constant pressure. So this will end up into delta H equals to delta U plus, now since like this can be expanded as delta P into V plus P delta V. Now since delta P is 0, you can simply write this as P delta V. So change in enthalpy can occur due to change in temperature, as I said, because change in temperature results in the change in internal energy. There can be phase change also, which results into the change in the energy, because you either supply the energy or you take out the energy to change the phase, or there can be mixing, or there can be reaction. So starting with the talk for phase change, or there can be temperature change. So for temperature change, the energy which is associated will be sensible heat, because whatever heat associated with that, it will cause some change in temperature. And whenever there is some change in temperature, that means there is no phase change, because phase change occurs at a constant temperature. And when phase change occurs, so like water, if you have water at 100 degrees Celsius also, and if you want to convert into vapor or steam at 100 degree, still conversion of water into its vapor or steam at this temperature also, you need to supply some amount of heat, which is nothing but latent heat used to change the phase of water into from liquid into vapor. So this is latent heat, and this is sensible heat. So now if we talk about the sensible heat, then there are certain constants which are associated to it. So whatever amount of energy you will need to require to change the temperature, so it will depend on mass of substance. Because for example, if you want to heat some amount of water, now if you have just a drop of water and if you have a liter of water, obviously the drop of water will be uh, easily evaporated also. It will vanish very soon. uh, or if you have a bucket of water and if you have just a glass of water, and if you want to heat like warm up the water, then changing the temperature of the entire bucket will take more time, or it will take more energy as compared to the glass of water. So obviously enthalpy or energy associated in that case will depend obviously on what mass you are taking, or the mass of substance. Another will be what change in temperature do you need. Okay, so delta T. And also there is some amount of characteristics of the material, which is nothing but its ability to store certain amount of heat. So based on what amount of heat it can store, like more the heat it can store, lesser will be its temperature rise. And so more heat will be required to raise its temperature. So it is nothing but a constant which is known as heat capacity of the system, which is characteristics to that particular element or particular system. So a heat capacity is Cp or Cv. This is at constant pressure and at constant volume. So constant pressure heat capacity is related to when you calculate enthalpy, and this is related when you calculate internal energy. So if you just a second. So if you are calculating heat capacity, so for example, this is nothing but it is the amount of energy that you will transfer to the system, so that the system having unit mass that is equal to 1 kg or maybe 1 gram, any unit you can consider. If you want to change the temperature of unit mass of that substance by 1 degree Celsius, then whatever amount of heat it is required, it is nothing but heat capacity. So the formula of enthalpy in terms of heat capacity is so heat capacity is nothing but H equals to M. So dH equals to whatever change will be mCp dt. So if you want to find out the change, then you need to, what you need to do, then you need to integrate dH. If you integrate, since mass is a constant term, you can take out mass. Now the heat capacity, it also depends on the temperature. It can depend upon temperature as A plus BT plus CT square and so on. So so if Cp depends on temperature, then obviously it will not come out of the integration. So it will be Ti to Tf Cp dt. And if it is a constant term, then what happens is delta H will be M. Cp will come out mCp. And if you integrate this will be T integration from Tf to Ti. That will be nothing but delta T. So at constant temperature, for constant heat capacity, this is the formula. For variable heat capacity, this is the formula. Now moving forward, this was all about the heat or energy calculation when you don't have any any chemical reaction, and there is just either the temperature rise of that system, or you are just encountering phase change. So this will be the case for just temperature change. Now, if you are encountering phase change, second. So when you encounter phase change, there can be liquefaction from solid to liquid. There can be vaporization from liquid to vapor or gas, and there can be sublimation, solid to directly gas. So whatever the amount of energy is required for this phase change is nothing but, as I told, it is nothing but latent heat. So you can add up the term latent heat for liquefaction, latent heat for vaporization, and latent heat for sublimation. So there will be certain value which will be available to you in the literature, and it is denoted by lambda. And for example, if it is for liquefaction, lambda L or whatever may be the notation, lambda V, lambda as S, and this is nothing but heat which is like latent heat. This lambda is nothing but the heat required to change the phase of unit mass. So if you have a certain mass m of the system, or if m of any material, then latent heat, for example, if you are vaporizing water having mass 2 kgs, and lambda V is the latent heat of vaporization per kg of water to be vaporized. So total heat that you will need to supply will be 2 into lambda V. So this is how it works. So this was all about the energy calculations, enthalpy calculations when there is no chemical reaction. So there can be some sort of chemical reaction also. For example, anyone would have observed that uh, for example, if you um, dissolve NaOH in water, then in there will like NaOH will be surrounded by water molecules and the temperature will be raised. So what is this? So it is the energy of dissolution. Now there are certain chemical reactions also where say for example ammonia formation 2 plus 3H, or sulfuric acid formation like SO3 plus H2O, sorry, gives H2SO4. So all such reactions, they are all either they consume energy or they release energy. Now if it consumes energy, they are termed as endothermic reactions, and these are known as exothermic reaction. So this causes temperature to decrease if you don't supply external energy, and this causes temperature to rise if the energy released is not absorbed by some external material. One of the most common example of exothermic reaction is combustion reaction, where if you have any fuel, like whatever you burn, like you have petrol, which is nothing but some carbon, some hydrogen, some oxygen, and so on. So it will be used up by, it will be it will react with oxygen to form CO2 and H2O, and there will be some amount of heat liberated. Now this heat is utilized to drive your vehicle. So what you are doing, you are converting one form of energy, which is chemical energy released, to drive a vehicle. So this is nothing but energy which is related to any reaction as well. So there are terminologies when there are reactions occurring. So one definition that you need to know, and one type of energy balance that you should know, is heat of formation. So what does that mean? For like, this is nothing but heat of reaction. So heat of formation is nothing but change in the enthalpy associated with the formation of one mole of molecule or 1 mole of compound from its elemental constituents. So what you do, say for example, if you want to form CO2, then if it is like C, it is elemental form, and O2 is the elemental form. Then from this, if you form CO2, then whatever the change in enthalpy you will see, it is nothing but heat of formation. And when standard comes, it is to be calculated at 25 degrees Celsius, 1 atmospheric pressure. So now from this heat of formation, there will be some delta H naught, like naught represents standard state, delta H naught for CO2, there will be some delta H naught for petrol, there will be some delta H naught for H2O. For O2 it is 0, because for any chemical in its original elemental constituents, it will be considered at 0. So if you want to find the heat of reaction, it can be obviously find from experimentation, and theoretically you can find out from the basics. For example, you can what you do, energy which is formed in the form of CO2 and H2O, and whatever will be consumed will be of the energy petrol. So delta H naught of CO2 plus delta H naught of H2O minus delta H naught of petrol. This will be the change in the enthalpy due to the reaction, and this is nothing but heat of reaction. So this is all you need to know from the lecture. Like, this is the important terminology. Now moving forward to the assignment. Um, so what is energy? Like, so energy is a qualitative property, or it is a quantitative, or mix, or maybe neither. Since it is a quantitative property because it has some units, joules, and you have some value by which you represent. So it is a quantitative property. Next question is, select the correct dimension of energy. Now energy is nothing but joules. It is represented in joules, which is having unit kg meter square per second square. And in that case, if you convert it into its dimensions, kg has dimension mass, m raised to 1. Meter has dimension length, so length square because it is having meter square, and second raised to minus 2, which is time, t raised to minus 2. So this is the dimension of energy. Moving forward to the next question, energy can be transferred. So this also we have discussed in the brief. So energy can be transferred obviously by the flow of heat, because it can change temperature, supplying or taking out of heat. This is nothing but flow of heat. It can change temperature. Also, energy is related to some amount of work, where work is nothing but force into displacement. So you are consuming some amount of heat, some amount of energy to change the position of that body. So this is also a kind of energy. So what you are doing, if you are trying to move a body, you are, whatever energy you are transferring to that body, it is transferred to do some work, that is displacement. So this is also a kind of work. And obviously transport of mass, So all the answers are correct in this question. So all of the above is the correct answer. Now, next question is match the following. So different forms of energy is given. So kinetic energy is due to the motion, anything that can possess. So if you see uh, any option which has relative motion, then kinetic, here water that is behind a dam, it is in motion obviously. So kinetic energy is related to option number 3. Potential energy is stored in the system when you are doing opposing the natural movement. So in that case, here if you see arrow hold on a string of archery bow. So if you are holding this, like if you are taking this string back to hold the bow, then what you are doing, this is the normal uh, position of this string, and if you are moving that backwards, there is uh, some tension and some amount of energy, because it is not the original position and you are going opposite to that force. So potential energy will be stored. So potential energy has correct uh, option match here is option 4. Then electric energy is due to the motion of charges, which is nothing but producing electricity. So for C it is 1. And radiant energy is related to the electromagnetic field. Option D has correct answer 2. So now next question is 1 joule equals to what? Like there is some unit change. So if you look into the unit, it is kilowatt hour. So watt has unit of joules per second, and if you there is kilowatt here, so it has to be kilojoule per second. So if you want to convert this kilojoule into joule, then what you will do, so kilojoule per second is the unit of watt, and you need to convert into hour. So you need to multiply it with time to convert into energy. So convert into joule, you need to remove kilo, so joule divided by 1000. And since you want this time into hour, so what you will do, you will convert this second into hour. So that can be done by dividing it with 3600. So 1 joule is nothing but, if you do the calculation, which is nothing but 1 by 1000 into 3600, it will come out to be 2.77 into 10 raised to minus 7. So this is 1 joule equals to this much kilowatt hour. Next question is, refer to the following figure and calculate the kinetic energy rate of water flowing through the pipe. So here we have a storage tank from which water is passing, and this is the volumetric flow rate because it is in meter cube per second, and it is flowing through this pipe having diameter 0.5 meter. Density of water is given as 1000 kilogram per meter cube. Now here you need to find out kinetic energy rate. So kinetic energy has formula half mv square. Now if you want to convert this into rate, what does rate mean? Any quantity per unit time. So if you want to convert this per unit time, then rate of kinetic change will be dependent on at what rate that material is flowing or water is flowing through the pipe. So to get the rate, what you will do, kinetic energy rate, let's say it is represented by dot. So half. So how can you incorporate rate in this equation? By converting, by taking mass flow rate instead of mass. So mass flow rate into V square. So what data you have been given is flow rate, which is volumetric flow rate Q, 0.01 meter cube per second. If you want to find out mass flow rate, then what you do, Q dot into rho. Rho is density of water, and if you multiply, it comes out to be 10 kg per second. So you find out mass flow rate. Now you need to find out the velocity at which water is flowing. Just a second. So to find out that, what you will do, you will utilize this data only, because and this data. So flow rate is nothing but it is the amount of water, which is meter cube of water, which is passing through this cross sectional area, and it is traveling this much length. So what does this flow rate mean? It is the amount of water passing through this much cross sectional area and traveling this much length. So this is the amount of volume which is covered per unit time. So you can divide the volumetric flow rate as the cross sectional area into the velocity. Velocity is nothing but length per unit time. So this is how um, volumetric flow rate can be calculated also, when you need to do some calculation based on this type of data if you are given. So volumetric flow rate is nothing but cross sectional area into length per unit time, which is nothing but velocity. So you have been given volumetric flow rate, and so from that, if you find out velocity, it is nothing but Q dot by cross sectional area, and it is nothing but 0.01 divided by pi d square by 4, and d is 0.5 given here. So if you calculate, the answer for this would be 0.01 divided by 3.14 divided by 0.25 square is nothing but 0.05 meter per second. So finding out kinetic energy rate, you just need to put up the values in the formula. So half m dot is nothing but 10, v is nothing but 0.05 ka square. So the answer coming would be 0.0125 approximately. There is no match in the option. This will be in joule per second, since everything is in SI. So you can change your answers accordingly. Next question. Match the following. So first is isothermal equation system. What does iso mean? Iso mean there is no change, and thermal means related to temperature. So what does isothermal mean? There is no change in temperature. So the system which has no change in temperature, you can see that refrigerate, because refrigerator, you supply some amount of you take out some amount of heat, so that some amount of temperature is maintained. So it is nothing but the example of isothermal system. Now open system. What is open system? Which is open, like open to surrounding, so that there can be exchange of mass as well as energy. So in that case, open system here is preparation of food in an exposed pan, because if there is pan, and if you are heating, there will be some amount of energy change. And what is the change in mass or the exchange of mass? It can be happening or it cannot be happening. But here you can say that if there is some amount of water, then water will be evaporated from that pan system to the surrounding, which is the atmosphere. So open system is preparation of food in an exposed pan. Now, adiabatic system is ice box in ice cream in the ice box, because you are avoiding the heat from the surrounding to go into the ice to touch the ice cream so that it does not melt. Okay, so you are not allowing any energy exchange, so that ice cream, the state or the phase of that ice cream, it remains intact. So the correct answer for adiabatic system is ice cream in the ice box. And isolated system. So isolated system means you are there is no change in mass and energy. So which is nothing but a hot tea in flask. So there is no change in mass also. There is no change in temperature also, or there is no change in energy. So for D, 1 is the correct answer. Moving forward to the next question. So these are the laws which you need to answer. So we already have discussed about this in the previous slides. So zeroth law means so energy. Yeah, so two thermodynamic systems are each in thermal equilibrium with a third one. Then they are in thermal equilibrium with each other. So for A, it is 2. First law is energy can neither be created and nor be destroyed, and it can just be transferred, converted from one form to another form. So, which is nothing but option 4. Second law is nothing but changes in the entropy in the universe can never be negative. So, this is a kind of irreversibility statement. So, option 1 is correct. And if you look into the third law of thermodynamics, it will be perfect crystal at 0 Kelvin will have 0 entropy. So this is the third law. Next question is calculate the enthalpy of a gas based on the following data. It has molar volume of 25 liter per mole and specific internal energy of gas is 5000 joule per mole. So if you look into the options, the energy enthalpy is given in terms of joule per mole. So you all need to keep everything in joule per mole. So internal energy is always already given in terms of joule per mole. And if you write the formula, which is nothing but enthalpy equals to U plus PV. Now you have been already given, which is 5000 plus pressure is given in terms of atmosphere. So since joule it is in joule, so convert this atmosphere and volume liter in meter cube and pascals, like which are the SI units of both. So if you convert 1 atmosphere into pascals, so it will be 101,325 pascals into volume is nothing but 25 liter per mole. So Pascal, like P into V has nothing but the unit of energy joule, and since volume is liter per mole, or if you convert into meter cube, it will be meter cube per mole. So this will come out to be joule per mole. So units of both U and PV are consistent now, because whatever you are doing, you are considering per mole of everything. So PV also has to be in per mole, and which is obtained from molar volume. So which is nothing but 25 liter per mole. And if you convert it into meter cube, which is meter cube per 1000 liter. So if you solve this, the correct answer you will get would be 7533.12 joule per mole. Yeah, so this is the correct answer. You can note down. Moving forward to the next question, change in the enthalpy is possible due to. So we have discussed this in the slides, and it can be due to, yeah. So uh, since enthalpy is the total heat content, so obviously if there is phase change, there is some transfer of energy. You supply heat or you extract heat so that it is converted from one phase to another. So obviously variation in phase is the correct option. blending of two or more solutions. So since blending of two or more solutions, say for example, one has temperature T1 out of two solutions and another has T2. And so if you mix both of them, there will be some amount of temperature change, and so there will be some amount of heat content change. So actually it will be added up and the temperature will change. So this is also corresponding to the change in enthalpy, and it is possible here. And obviously, if there is some temperature change, there will be some change in enthalpy. So all the options are correct. Now moving forward to the next question, select the correct correlation between specific heat at constant pressure and specific heat at constant volume CV for liquids and solids. So since Cp and Cv, this represents at constant pressure. This is used when you need to calculate enthalpy, and this is at constant volume, and it is used to calculate internal energy. Okay, so now all this terminology at constant pressure and constant volume, they are more related to gas, because this all are variable for gas because it can be changed. For liquid and solid, since they are incompressible, you can consider that the effect of pressure and effect of volume will be negligible. In the case of gas, Cp is related to Cv as Cv plus R. R is the universal gas constant here. And if you look into liquids and solids, so Cp will almost be equivalent to Cv, because the effect of pressure and temperature volume can be neglected. So C is the correct answer. Next question is, a stream of nitrogen flowing at 100 kilomole per hour is heated from 303 Kelvin to 373 Kelvin, and calculate the heat transfer in kilowatt. So which formula you will be using? I had shown you the formula. So the heat capacity is given as Cp, and you can see that there is some variation of Cp with respect to T. So delta H in that case would be M integration from Ti to Tf Cp dt. So yeah, mole, it is given in kilomole per hour. So you will say that the energy that you will obtain, it will be joule per time. Okay, it will be in hours. Okay, so you can say that this will be a kilowatt, and for that you need to consider mass flow rate. So 100, and since you need in watts, which is joule per second, so time has unit seconds, and keep kilo as it is because you need in kilowatt, so keep kilo as it is, and convert hour into seconds because uh, the time which you need is in seconds. So since it has hour, so divided by 3600. Now integrate it from 303, which is the initial temperature, to 373 Kelvin, and you put up the value of Cp, which is 229.5 5.141 10 raised to minus 3 T plus 11.18 T square plus like into 10 raised to minus 6, 4 like minus here 4.968 10 raised to minus 9 T cube dt. If you integrate this, there will like what this term will be 29.59 T minus 5.1 10 raised to minus 3 T square by 2 plus 11.18 10 raised to minus 6 T cube by 3 and minus 4.96 10 raised to minus 9 T raised to 4 power by 4, and this has whole multiplied by 100 by 3600, Now, if you put up the values of integration from 303 to 373, and if you if you do final minus initial and calculate the answer, then heat transfer in kilowatt would be 56.27. Moving forward to the next question, for an ideal mixture, the enthalpy of mixing is 0. Next question is, internal energy for real gas is a function of temperature as well as pressure, because for ideal gas the pressure is very low and you can neglect the interaction, so there is minimal effect of pressure on real ideal gas, whereas in the case of real gases there is some effect of pressure which results into its deviation from ideal behavior. So obviously its internal energy will depend on temperature as well as pressure. Next question is, select the incorrect answer. So the addition of heat to a substance increases its internal energy. So this is the correct answer. Work done on the system increases its internal energy. So work done on the system means you are giving work or giving energy to the system, so it will increase the internal energy obviously. Now, internal energy of a real gas is a function of both temperature and pressure, so this is also correct. And internal energy of ideal gas is a function of both temperature and pressure. It is incorrect because it does not depend on pressure. Option D is correct for this question. Next question is, calculate the standard heat of reaction at 298 Kelvin. So for this I had given you the equation in the previous slides, how you calculate standard heat of reaction. So what this is, this all are standard heat of formation. Okay, so if you want to calculate standard heat of reaction for this system, then it will be nothing but delta H naught for Na2O Fe2O3 plus delta H naught for CO2 minus delta, this is nothing but reaction for entire reaction, minus delta H naught for Na2CO3 because they are getting consumed, and minus delta H naught for Fe2O3. Sorry. If you put up the values for Na2O Fe2O3, it is minus 1412.2 plus for CO2 it is minus 393.51 minus for Na2CO3 minus 1130.68 minus Fe2O3 has minus 1817.3. Calculating and solving this, you will end up getting 142.27 kilojoule per mole, because all the heat of formation has unit kilojoule per mole. Next question is, ideal gas law has approximate validity at dash temperature and dash pressure. So this was earlier also discussed. Since at low pressure the molecules are very far away because the concentration of gas will be very less, so chances of interaction will be less, and you can consider that gas to be tending towards ideal gas. So low pressure favors a real gas to be considered as ideal gas, and obviously at high temperature molecules will have more energy and so they will be far away. So high temperature and low pressure, they will favor real gas to behave as ideal gas. Next question is, consider a closed system that is cooled reversibly from 150 degrees Celsius to 50 degrees Celsius, and if the system does not work, which option is correct? Now, since you are cooling the system, obviously its internal energy will decrease. So what you are asked here is about internal energy and about entropy. Um, here, since um, temperature decreases, internal energy will obviously reduce, so internal energy decreases. And since it is cooled reversibly, so what does that mean? The wastage of energy will be zero. And since S is nothing but dq by t, which is waste of, like, which is not consumed, so in this case this will be zero, and so that change in entropy delta S would be zero, so entropy remains constant. Next question is, for ammonium synthesis reaction, like ammonia reaction, this is the standard heat of reaction. So standard heat of reaction means heat of reaction per mole of what product is formed. So actual reaction is this, if you balance it, and to form 1 mole of ammonia, what is the amount of heat generated? This is the amount of heat. Now and here it should not be standard. Then calculate the heat of reaction for the reaction this. Now since you are producing 2 moles and this is for 1 mole NHC formed, so for 2 moles to be formed, it will be 2 into minus 46110, which is the heat of reaction. So correct answer is option D. Next question is, dash is the equivalent to the total heat content of the system. So this is nothing but the definition of enthalpy. So correct answer is enthalpy here. So thank you so much. That's all from my side today. So if so, I can end this session here. I will close the meeting. Thank you, everyone.